Okay, welcome back. What I want to do now is to continue with what we were doing before. All I'm going to do here is just recap quickly. Okay, so this you have seen already in motor principles. Okay, so I'm not going to stay too long on it. Okay? And that you will have seen already. All this is, I'm just doing a brief recapping session. Okay, excuse me while I put my teeth in. Right, this is what I want to pick up on today. And again, I must thank this guy, DJ Dunn WW, who provides a lot of free study on this kind of work and material at a high level. Okay, his work is excellent. Okay, now remember that you cannot go to his work, his website, and just think you can copy of the work. It doesn't work like that. It actually has to be done, and this is what I'm doing here with you now. I'm presenting you with some material which he has produced in a manner which I hope you can find more digestible. But remember, you have to write the work down yourself. You have to take and extract the questions and look at the work from that point perspective. So for today, we're doing motor principles, and I'm on motor principles 2. Okay. Right, so what I want to look at now is we have here the pictures below show the main parts of a motor where the rotor is the armature. Okay. And this is your rotor. At each end there are bearings. Okay, let's go in and so you can see it fully. Each end there are bearings. These bearings here has a tendency to wear over time and often will need changing or replacement. When these bearings wear down, this here, this body, this rotor begins to rub against the inside of the field housing. I'm just going to call it field housing for now, okay? And when that happens, your motor is knackered. Okay, so one of the things that you will find that people does or maintenance engineers has to do is to maintain and these bearings here to be lubricated so it minimizes the wear on the armature. Okay, now these are the brushes. That's your commutator. These are the brushes which makes contact with your armature, and these provide the source of current voltage, if you like, as well, because without a voltage you won't have a current, but I could be wrong. Okay, so brushes touch making contact with the commutator, which provides your current for your driving force in regards to the field on your armature winding. Okay, or armature winding if you prefer. And here now, let me make sure I can read this out, and I want you to be able to see this in full because you have to read this yourself as well. Powerful motors, they are electromagnets with coils. The poles called the field windings. The stator, excuse me again, form a magnetic circuit, and the flux crosses the loops on the armature as shown. Now what you're looking at is these windings which crosses the core of the armature windings. The strength of the magnetic flux can be changed by changing the current. So you can change the speed of the armature within the motor by changing the current. That is by reducing or increasing the current. Okay. The rotor in the diagram would be called the armature. Okay, and that is what we're looking at here. In this case, this is the armature. Okay. Now let's go across a little bit more. And we're looking at this now, okay? So let me just see if I could bring this up a bit bigger for you to make sure that you can see it in full, okay? And let's just get a big picture of that, okay, in full, okay? Okay. You can see that there, that. You can see almost how that has okay. And this in here, what you see here is it's a sealant, it's varnished. Okay, so the couples are varnished with an insulating material substance that prevents the coils from shorting out. Okay, and they're connected at your relevant commutator connections. Okay, let me just go across and bring the other part in. Okay. Now this would be your stator here, okay, and that again here would have coils within it, okay, and these coils again would produce a magnetic field within the stator. So you got poles, main core, field windings, and these windings loop in and out, okay, again and again, okay. Let me just take this down a little bit so we can get back to a normal size. And I'll move you in. Take it down a bit more. Okay. 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 Good. Now I've given you here. Now you need to read this in full. So picture shows parts of a motor where the rotor is the armature. Okay. The magnetic poles may be permanent magnets, but in more powerful motors they are electromagnets with coils wound on, form a magnetic let me make sure I know where I am. Wound on okay, wound on, that's interesting. Wound on the poles called field windings, the stator and rotor form a magnetic circuit, and the flux crosses the loops on the armature as shown. The strength of the magnetic flux can be changed by changing the current. The rotor in the diagram would be called the armature, and that would be your rotor. Sorry, it's okay. This little section here gave me a little bit of issues, okay, initially, but it's okay. I think I've found the little pieces together. Ouch. Now here we have a lot more information. You can see the typical construction and explanations at this web location. Now if you go to the web location here as it's given, okay, it'll give you a lot more information and allows you to try to interpret and understand in more detail what we're trying to show you here. The next diagram shows the typical schematic representation of a motor. Current has to be supplied to the field windings to produce magnetic flux. Current must be supplied to the armature to produce the torque. Note the brushes used to contact armature. Okay. So here you have, now again, these diagrams here, you need to draw them up out in full. Okay. You need to draw them out in full. Let me just make this large enough for you to see it. Okay. Okay, so you can actually understand and see. Okay, 1 second. Oh, crumbs. I was calling you at the wrong time. Sorry, it's just the missus making a lot of noise now, calling me in the middle of my session. Okay, right. So here you have the diagram. Let me step back a little bit, making sure that we can get it in full. Yes, we can. Okay. Now you need to draw these out. So what you have here is IF, field coil, brushes, which I showed you already, current in armature, voltage, and EA. The electromotive force in the armature, okay? And it's a DC supply. Now let me just take it down so we can get back to normal size, okay? Okay, good. Okay, now let me just bring this up as well, a little bit larger. Make sure that you can see it, okay? You don't have to strain your eyes to read it, okay? Like some information you have to, okay? Now, you can see here is IA equal armature current, V equals supply voltage, EA is electromotive force at the armature, RA equals resistance of the armature coils, EA equals V minus IA RA, okay? If the armature windings were perfect conductors, then EA equals V. If IF equals field current, T equals torque, N equals rotor speed in revs per second, okay? Okay, let me just make sure I've got this. Let me just take this down back to size and we can get everything in. Okay, thank you. Okay, yes, I think I have. Okay, yeah. Okay, now when we look at this, we need to consider the theoretical aspect of this. And here we're looking at theory. Right, so let me bring this up a little bit larger if I can for you. So again, we don't have to be looking or training ourselves or our eyes. Let me make sure I can get this into full view. Nope, it won't go into full view. Give me let me drop it down a little bit too high. Okay, that's good enough. Okay, that should be good enough. Okay. The conductors in a motor pass through the flux from the poles, and so an EMF is generated in them that opposes the flow of current from the source. The voltage applied at the terminals to make the motor rotate is V, and this must be larger than E to overcome the resistance of the armature and brushes. So it follows that V equals EA plus IR times RA. Okay. So you need a voltage to overcome the initial resistance of the internal force when you have set up those magnetic forces. And that then sets about creating your rotation in respect of your theory in regards to the formula given. Okay. If the conductor is part of a loop of radius d over 2 meters, then the torque produced is T equals F force times distance divided by 2. Now T is the torque, equal F is the force, D is the distance, or the length of conductor within the armature or the stator, or within the field itself. Okay, that makes it the field, and that would be Newton meters. The force is F equals B LV, and B equals theta over A, where theta, I call it theta, you may call it something else, is the flux in Weber, and A the area of the flux path. Substitute for F and B, T equals theta L I D over 2 times A. For a given, now for you guys there at your level, you should know, familiar with applying the solution to this yourself actually. Okay, I'm some of you might even spot my deliberate errors. For given motor, the only variables are the flux and the armature current, so the equation reduces to, now T equals K1 theta IA. The electric power consumed by the armature is P equals EA times IA. And remember that this bit here is for you to apply for yourselves, okay, because T represents the torque being generated by the motor itself. Okay. The electric power consumed by the armature is P equals EA times IA. Now power generates what? If you're going to generate power in anything, you're going to generate heat. And once you have P, you need to bear in mind that where you've got power, you're going to get heat. And the problem you're going to have here is that if you begin to get heat in your motors, okay, let me go back a little bit, begin to get heat in any of this area, or in any of this area here, it begins to affect the coils themselves, and the coils themselves can begin to give you problems. So you need to be sure that you have means of cooling your motor to make it safe and for it to run consistently without overheating or too much power consumption being wasted or used for the wrong purpose. Okay. Okay, this is motor principles 2. Okay, and I'm going to stop there for now. Okay. Okay, and I hope you found this useful. Now what I want to look on next is the mechanical power produced is P equals omega T equals 2 phi NT. Okay, now I'm not going to be breaking this down to you guys because you're doing HNC, so you'd have done a lot of this yourself. You now need to be doing the calculations. You need to write out the formula. You need to write down the elements and the parts that go to make up the questions, and make those just for yourself to work for you. Okay, that's what it's about. Okay, thank you for your time, and let me just recap slowly. Okay, let me just go back a bit, make sure we can get it all in. Okay, come here. Okay, so I'm going to be there, and thank you. Okay, thank you for your time, and have a good day. And again, all I'm doing now is just bringing all of this into play to show you that you've used this all previously, and that it is all linked. Okay, right, thank you. I'm going to go back now. It's important that we recap on each session so you can see what you have done and what we need to be doing ourselves. Okay, right, thank you. Good. Okay, right, thank you. Good night for now, and we'll talk again soon. Bye bye.